I will try to give you an overview of what we have done with a group of other people regarding a machine learning algorithm that we developed to look for feature in the gravitational wave data coming from core-collapse supernova. And the idea will be also to include the neutrino as a trigger and additional information to this type of analysis. So this is the outline of the talk. I will start just reminding everybody the crucial milestone in the multi-messenger astrophysics. So I'm talking about the event of GW 700817. And then I will briefly talk about the neutrino astronomy and why it is important to include also this information in the analysis. And then the remaining time, I will focus on what we actually have built and done with this algorithm. So as you know, the August 17, 2017, there was the detection of the gravitational wave coming from the merger of binary neutral star system. And 1.7 seconds later, there was the coincidence of a short GRB that was seen from the detector by Fermi and GBM. That was not the whole story. In fact, there was a plethora of other follow-up observations, starting with the first optical telescope that localized the host galaxy of this event. That was the SWAP telescope in Chile. And the galaxy is the NGC 4993. These are all other optical telescopes. And as you can see here, also X-ray and radio 9 days and more than 60 days after were found. So the complete electromagnetic spectrum was covered. And so this was really the beginning of the multi-messenger astrophysics because following the gravitational events, we could cover the complete set from the gamma ray to the X-ray, ultraviolet, infrared, and radio. So we could also identify the position of the host galaxy to be 130 million light years distance. And the other key feature of this event was the creation of the kilonova. So this star that is 1,000 times brighter than a normal nova, that provided with clues to the origin of elements like gold and platinum. This is just to remind you what was the behavior of the brightness of the kilonova versus the wavelength due to the radioactive decays of heavy elements, and so it turned from the blue, that is the decay due to the iron group, to the red emission, in which heavier elements were considered. So here, just to show you what the optical telescope was seeing, this is how bright was the kilonova in the day of the event, and this is when it gets fainter about a few days later. And this is exactly the same plot, but a static version of the spectral luminosity versus wavelength of the kilonova that we just saw. Here, I just wanted to point out that for the first time, the LIGO-Virgo collaboration was able to shrink the error region in the sky. That was still big for telescope or satellite, but was the best ever achieved. And it was of about 26 square degrees, and this is the dark green color, and you see superimposed the error region covered by the integral and GBM. And this is the point in which the SWOP telescope pinpointed the position of the Earth galaxy. So this event was extraordinary, was followed by more than 200 instruments from ground-based satellite telescopes around the world. And we also perform an analysis looking for neutrinos in coincidence with the same event. Unfortunately, we couldn't find any coincidences. And here you can see this is the position. The red one is the 90th percentile of the gravitational wave event, and the cross is the exact position of the Earth galaxy. And here you see the cross are coming from they are neutrino candidates. Sorry, it's a bit blurry. And the diamond shapes in blue are instead candidate coming from the Antares detection. And so you see, none of them is in coincidence with the same event, and so we are still looking for this type of coincidences. Of course, it was possible to make different constraints. First of all, to constrain the speed of the gravitational wave, that is between -3 times 10 to -15 and 7 times 10 to -16. The second important achievement was the evidence for the kilonova model, explaining the isotropic thermal emission produced by the radioactive decay of the rapid neutron capture elements. And so the blue emission was the one dominated by the iron group elements, while the red one was dominated by the element like the lanthanide formation. The other constraint or measurement that was done was the one using the gravitational wave as a standard siren. And so knowing the luminosity distance and the redshift, we could compute the Hubble constant that is in agreement with what the Planck collaboration found. And last but not least, it is also possible to constrain the neutron star equation of state, and so find that the data are consistent with a softer equation of state. So in other words, a more compact object that was merging. So now I want to pass through the neutrino astronomy and start with the reason why I want to talk about it. So this plot of distance in megaparsec over energies is in electron volt is telling you that 20% of our universe cannot be seen through electromagnetic counterparts. And so the only way we have to constrain this type of sources that we think are cosmic accelerators are by using gravitational waves and neutrinos, because they can travel unobserved over cosmological distances and carry information of the inner engine of these sources. So instead of looking for charged particles like protons that can be deflected in the magnetic field, or photons that can interact with the CMB photon producing coupled E plus E minus, we want to consider the neutrinos that don't actually interact between the source of production instrumented volume.
Can you stop for a second? I think you were frozen. Could you just repeat what you said, like how on your last slide?
Which one? This one?
Yeah. So I think we missed you out of around half of the slides. So if you could just repeat, please.
This slide, is that correct?
Yes,
okay.
Exactly.
Now here I was okay. Here I was just saying that instead of looking for charged particles that are deflected by the magnetic field and gamma, so photons that interact with the photon of the CMB, producing E plus E minus, we want to consider the neutrino as a probe to look for the inner core of these cosmic accelerators. And the issue is that it's not easy to detect them, because on the Earth's surface, the cosmic air showers produce a huge background of charged particles, and even going in the deepest mine shaft, there will be a non-negligible flux of muons from cosmic ray showers, and so the neutrino telescope have to look for neutrinos that pass through the entire Earth. So they use the Earth like a shield against all particles except neutrinos, and so the neutrino telescope seek out upward moving muons that are created in the interaction of the high energy muon neutrinos with the matter around the detector. So it exists the global neutrino network that is composed of 4 different collaborations. The type of detector is it's exactly the same. It's a 3D array of photomultipliers. So the difference between the detectors, apart the volume and the size, is the deployment site. So in the case of Antares and Chemtranet, they are deep in the Mediterranean Sea. Baikal detector is in the Lake Baikal. Instead, IceCube is under ice at the South Pole. So let's start, we just briefly talk about IceCube and Chemtranet. So this is the site where IceCube is. And when you stand there, you stand over a few kilometers of ultra clear ice that cannot be produced, not even in lab. And that's because it was snow that fallen 200,000 years ago, and then create this super clear ice. Of course, so all of these are extreme environmental places in which it's really difficult to deploy an instrument. And so here you see the IceCube, that is this 3D array of photomultipliers. This is one photomultipliers, and the total number is more than 5,000 in the complete configuration. And the instrumented volume, it's order of the kilometer cube. I just want to briefly show you how difficult it can be to deploy such an instrument. So in the first 200 meters, you use a regular drill. To follow, then to continue to have the hole, you need to have hot water pump that is pumping water at 90-degree temperatures. And so in this way, you can reach a hole with a length of 2.5 kilometers in about 2 days. And the point is that when you have done the hole, you have to deploy the strings, that is a cable in which the photomultipliers are connected. And so now you will see, apart from all the supportive material that you need to survive there, You will see in a bit the boxes in which these photomultipliers are shipped and bring to the site, and then you will see them. So this is when the second the hot water drill is coming out, the one that it uses warm water to dig the hole. And then what you will see is the people deploying the photomultipliers. And that's the last time you see your detector, because then the water will ice again and it will stay there forever. So this is the complete string on the shelves, and this is what exactly I was telling you about the deployment of the photomultipliers. Okay. Of course, changing environment, like in the case of ChemTreeNet, you are not working anymore to drill holes in the ice, but you need to deploy the instrument deep in the water. And so apart from a big ship, what you need is something to deploy the string. And the ChemTreeNet collaboration invented this launcher in which the complete string is inside. So what happens is that the string through a robot is connected to the seabed, and then through an acoustic signal, it gets released. And so this launcher starts to unfurl, and the string will be completely out of the launcher in this vertical configuration, and the launcher will be collected from the people on the ship for the next deployment. So just a couple of seconds of the starting of the unfurling of the launcher of ChemTreeNet. ChemTreeNet, as I was telling you, is a detector that is under construction in the Mediterranean Sea in two different sites. One is in 2,500 meters deep in the Mediterranean Sea in front of the French coast. Instead, the other site is 3,500 meters in front of the Sicilian coast. And so it is important to have these two instruments, one at the North Pole and one in the North Hemisphere and one in the South one, to have a complementary view of the sky. And so when ChemTreeNet will be completed, the instrumented volume will be few times the one of IceCube, so the sensitivity should also be better than the actual sensitivity of IceCube. So what they wanted to detect, as I was telling you before, is the Cherenkov light due to the muon that is moving in the water or in the ice faster than the speed of light. So it's created this characteristic blue emission that is called Cherenkov light. And this is one of the reconstructions in which you see for each of the sphere that you see this as that's a photomultiplier, and bigger you see the sphere, bigger is the number of photons that have been detected. So IceCube was already well known for the discovery of the neutrino diffuse flux through the 28 events, high energy neutrino events, and the most famous one were BERT and Ernie. I want to show you the detection of BERT that was 1.04 PeV. And you don't realize how big is this event that had more than 300 optical sensors involved and more than 100,000 photons. But if you superimpose the event to the Madison city, that is the headquarters of IceCube, you see that only in the horizontal part you see more than 4 blocks, and it's even more in the vertical one. So that's really a huge event, even in not only for the energy but also in dimensions. And they decided to name each of the event. In this way, they can remember better the feature of each event. And most of the names are coming from puppets, non-puppets. That's the event I wanted to talk about, September 22, 2017. So almost a bit more than a month after the GW700817. This was the GCN notice that went around, and also in this case, there was a huge follow-up campaign to try to find association of other probes with the neutrino event. And what happened was that both Fermi and MAGIC detected the emission of TeV gammas coming from a flaring blazar in a position that is within 0.1 degree. So exactly in the position of the neutrino event. And that was a huge breakthrough in the neutrino astronomy, because it was possible to complete the spectrum of this source, that is the Texas 0506 plus 056. So I'm interested in core collapse supernova, and as you know, and you heard a lot of talks in the last days, that's the result of iron core of a massive star in the main sequence. It's supposed to leave a remnant that is a neutron star or a black hole, and the energy released is order of few times 10 to 53 ergs in the gravitational collapse. Mostly, so about 99%, is radiated into neutrinos. The other broad categories is the so-called type 1A, that is caused by the runaway thermonuclear burning of white dwarf fuel to nickel. In that case, no remnant is left behind, and the energy, the estimate of the energy released is roughly 10 to 51 erg. There was a detection of several neutrinos from a supernova in 1987, in particular in February 23, 1987. And the supernova is the well-known supernova 1987A, and the 3 detectors that made the detection were Kamiokande, EMB, and Baxan. So that's to say that we have seen already neutrinos from supernova, and we hope to see them soon enough. We know that the massive stars spend the majority of their life burning hydrogen, and the product settles in the core and will burn when temperature will be high enough. This process goes on till iron, and the iron core builds up in the center of the star, and is supported by the electron degeneracy pressure. When the radiation pressure doesn't balance anymore gravity, the collapse starts, and the implosion of the inner core is stopped when the nuclear density is reached at the center with the formation of the protoneutron star. And so the inner core bounces back and creates pressure waves that propagate outwards in radius and mass. And so shortly after, neutrinos carry away energy from the post-rock layer, and only in the case in which the heating of the neutrinos is strong enough, the shock can be pushed outwards and the supernova explosion can be launched. So according to neutrino-driven mechanism, neutrino are key to power supernova outbursts, and at the same time, gravitational waves are generated in the inner core of the source. And so these messengers can carry direct information of the inner mechanism. What we wanted to do is to engage in this challenge and write a deep learning algorithm to look for core collapse supernova feature in the gravitational wave data. So reading this paper was really interesting because here what the authors have done was to produce a numerical simulation of a massive star, a 15 solar massive progenitor, and use different equation of state from the soft one to the stiff one. And what you see here are two time frequency plots in that simulate the gravitational wave data and the emission of this simulation. And here you can see this is on the left you have the soft equation of state, and on the right you have the stiffer one. And you can see that there is a clear feature in the of this ramping up in this time frequency plot that is shown also in the other plot, and this is due to the excitation of the G modes, and so the evolution of the proto-neutron star. Instead, this one that is tagged with B is called standing accretion shock instability, or SASI for short, and is present only when they use the software equation of state model. So we have of course different scenarios. What we are interested in is the first one, so the neutrino-driven core collapse supernova, in which is it possible to clearly discriminate the ramping up of the G mode that is describing the evolution of the proto-neutron star from the SASI event, for example. Since we cannot afford to have to run 3D simulations of core collapse supernova for months, the idea was to use a phenomenological template to mimic the ramping up of the G modes in the core collapse simulations. And so the idea is that the proto-neutron star is in quasi hydrostatic equilibrium, and any perturbation will excite the eigenmodes of the system, and in particular the G modes. So for example, by convective motion or through SASI. So the gravitational wave emission is modeled as a damped harmonic oscillator with a random forcing in which frequency varies in time. And this is an example of the waveforms that Pablo produced. In the upper left side, you have the plot of the strain versus time. In this other plot, you have frequency versus time, in which you can see the arch structure to model the G modes. And in the table, there is the parameter space that we use for the simulation. And so we have this flexible parameterization for the frequency evolution, and we also included the distance as a parameter. And that's a difference between this work and the previous one. So what is the idea? The idea will be to use the neutrino as an external trigger to open a window in the gravitational wave data, and to use the machine learning algorithm to recognize the signal in coincidence with the neutrino. So to be able to have a machine that works in this way, we need to create a time frequency plot as the one that we just saw, to feed the machine learning algorithm that will be trained, validate, and then will analyze an unseen set of data to classify them as signal or noise. So the result I will show, they considered, they run on the second observational run of LIGO-Virgo. And so here you have the two positions of the LIGO detector. One is in Hanford and the other one is in Livingston. And the Virgo detector is in Italy. Recently, also, CAGRA joined the radiation wave observational network. But in this case, we only use data from the second observing land. So CAGRA is not yet included. So to produce the time frequency plot that we have to feed to the deep learning algorithm with, we use an excess power algorithm that is called coherent wave burst that is developed inside the LIGO-Virgo collaboration. And what it does is to decompose the data stream in different time frequency resolution levels. And so the time frequency decomposition of the data at the chosen level is considered as the input as the neural network. These are a couple of examples of what the time frequency plot looks like. Why do we use machine learning algorithm? This part of the machine learning is booming at the moment. So it's not only used by scientists in database mining or application that cannot be programmed by hand, but is also used in self-customizing programs like the product recommendation of Amazon and Netflix. There are several kinds, from the classification, denoising, or the optical character recognition. What it consists of a multi-scale hierarchical structure of different layers that can be linear or non-linear, but each layer is composed of neurons. And what it does is to weights iteratively update a gradient descent algorithm to minimize a cost function. And in particular, we use convolutional neural network, that is a particular kind of machine learning algorithm because it's biologically inspired. So essentially, what we wanted to mimic is the relation between the eye and the brain. So while the eye creates the upside down image on the retina, then the retina converts the light into a neural signal and sends the information to the brain that has to elaborate the data and build the final image. And that's exactly how the convolutional neural network works. So starting from the pixel, it looks at the edges, combine the edges, and then complete the object module. The training, so the way in which the machine is learning is done in a way that is necessary to minimize a loss function, while when the machine is calibrated, so the learning phase is done. There is the last stage in which it has to be tested on unseen data, and that's the part in which you have the model and the predicted class. So to wrap up, you need to generate the data that have to be consistent with the problem and find a way to map the property of the system. Then the data are split in different sets, usually training set, validation set, and test set. So to train the algorithm, you use the training set. Then to refine the model that the algorithm has learned, you use the validation set. And then to estimate the model generalization, the code has to be evaluated on unseen data, that is the test set. In our case, we wanted to discriminate between detector noise and signal plus noise. And what we use is a GRB multi-detector scalogram as an input to the neural network. And what we wanted is to detect the signal in at least 2 detectors out of 3. So this is what RGB means. So we assign to each of the detector involved a color. LIGO-Hanford as red, LIGO-Livingston green, Virgo blue. So here you can see the time frequency plot in the case of Hanford in the red channel, time frequency plot in the case of Livingston, and the blue one is the case of Virgo. And you see here there is this ramping up. This is again something that is coming from the simulation of a core collapse supernova, because it's again this arc structure. And so in these 2 cases, you see the signal, the simulated signal. Instead, in the blue channel, so in Virgo, you don't see any. So when you mix them together, you should see a signal. So the signal, the feature that you're looking at, that is yellow, and exactly what you see over here. Of course, changing the channels, you could have the 3 detector, and so the G modes structure will be white or light blue, depends from the detectors that can see the signal. This is just to show you what the difference between only noise and signal plus noise looks like. See, in this case, the signal is shifted, is in this bin instead of being here like in the previous case. So the architecture of our algorithm is a reduced version of the Inception ResNet that it works in the Keras framework based on TensorFlow backend. Is 30 times more complex than the previous network that we used. And the task is a multi-class classification problem with 2 classes, the event class and the noise class. And so we use binary class entropy. Just to give you an idea, the training and the validation phase in real detector noise was performing a bit more than 2 hours on a GPU, while predicting the test set takes about 3 milliseconds for each 2-second long images. Each of the time frequency plot is composed of 256 pixels in time and 64 in frequency, times 3 because 3 are the detectors. And the coverage of the frequency band is between 0 and 248 Hz. And the time of the image is 2 seconds. We train about more than 98,000 parameters, and we use decreasing SNR. So while in the previous attempt we have done we use the algorithm on we test the algorithm on Gaussian noise. In this case, we only use real noise, real detector noise of the 7 observing LAN, and in particular August 2017. So the training set is composed of phenomenological waveforms, in particular 70,000 images for each distance between 0, 2, and 3 kiloparsec and random sky localization. 75% of this set is used for the training, and 25% is used for the validation. The blind set is again composed of phenomenological waveforms, 260,000 images with distances chosen in a uniform distribution in the range between 0.2 and 50 kiloparsec. This set is not involved in any training or validation procedure. The test set instead is composed of 3D numerical simulations from the literature, and in particular 65,000 images with distance between 0.1 to 15 kiloparsec. And the period that we use of data is about 15 days of coincident time among the three detectors, and we use to generate about 2 years of time-shifted data to train and test the neural network on the noise class. So the output of the network is a probability vector, theta, which contains the probabilities of the template belonging to one class or the other. And the classification task is performed according to the decision threshold, theta star, and so the template will be classified as an event class only if its probability overcomes theta star. In the plot that you will see in the next slide, I will show the efficiency and the false alarm rate of the convolutional neural network.
9 minutes.
Yes?
9 minutes left.
5 minutes left. Okay.
Thank
you. Okay, thanks.
You're good.
So the additional information that I want to add is that we also included a weight, and in particular W equal 2. So for us was 2 times more important to correctly classify noise rather than the event class. And this is the comparison between the efficiency and the false alarm rate that we have in comparison with the previous work that we have done. This is instead a snapshot coming from the validation process, in which what you want is to maximize the efficiency while minimize the false alarm rate. So this is the first plot of the results that I wanted to show you. Here you have on the vertical axis the probability density versus theta. And you have 3 different histograms. So the green histogram is the one that picked at 0 because it's composed of detector noise. And the other 2 picked at 100 because they contain simulated data. I show in this plot because I want to show you the robustness of the decision threshold, theta star equals 65%, in which we are able, so picking this decision, we are able to remove the majority of the detector noise and lose only a tiny bit of signal. In the case of the efficiency of the convolutional neural network versus distance in kiloparsec, here you see that we are able to detect a core-collapsed supernova at 1 kiloparsec with more than 85% in efficiency. Instead, if we want to go farther and arrive, so consider larger distances and go to 15 kiloparsec, the efficiency drops to 60%. If we want to see the plot, the efficiency as function of the network SNR, what you see is that for SNR that is bigger than 15, so roughly 8, SNR 8 for the single detector, we have an efficiency that goes from 70% to 100% when the network SNR increases. And with this, I will conclude. So we are trying to to make the point that this development of the deep learning algorithm is working on this feature, and of course it's open to multiple possibility and extensions. So, for example, we could include the SASI feature, and we can also consider the magneto-rotational case, so the other scenario that I was telling you about. And of course, that will be something that we can even improve more with the 3G detectors that we will have hopefully soon. So thank you. That was all for me.